All right, so let's get going on today's class. So today we're going to have our final class and wrap up Chapter 13, Judgment, Decision, and Reasoning. And before we get to that, just want to make sure everybody's aware of the final exam that is coming up. So this is going to be Thursday, May 2nd, in class, during class time. The chapters, Coglabs, and lectures that will be covered are chapters 11, 12, and 13. So everything since exam 3, this is non-cumulative. Just it's a final exam, but in reality it's exam 4. So everything since exam 3, language, problem solving, judgment, decision, and reasoning. The Coglabs, the ones that we've taken a look at, categorical perception identification, waste and selection task, and the Monty Hall Coglab, which we'll look at today. And then all the lectures since the exam number 3, including, don't forget about the one where we started language before we had exam 3, just because of scheduling issues, and then going all the way up to today's class. All right, and the format unchanged is still multiple choice, still 2 sections. Section number 1 covers material that is not covered in class. Section number 2 covers material from the readings as well as lectures and Coglabs. Section number 1, recognition type questions only, and will only be worth 1/3 of your score. Section number 2, recognition type questions as well as application type questions, and that is going to be worth 2/3 of your score. So any questions on that before we get to today's class? All right. So what we're going to do today is we're going to wrap up our look at cognitive psychology by taking a look at game theory. We're going to have the Pirate Booty Challenge again revisited, this time with a slight little tweak. Then we're going to take a look at another game theory challenge to ask the question, are people rational? And that's the 2/3 of the average problem. And then we'll wrap it up with the Monty Hall problem, look at that, and also a little bonus section on Marilyn Savant and confirmation bias and how it got kind of played into a sexist reaction to one of her articles. All right, so game theory. Game theory is a subcategory of decision theory, and it applies when an individual's success in a particular decision-making situation depends upon the choices of others. So that's the new thing that we have here. That's the new wrinkle that we have. Your success in a game theory situation depends upon what other people actually do. So far we've seen some examples of things that are not game theory. So the Tower of Hanoi is not game theory. The solving the discs stacked on top of each other, that doesn't fall under game theory because there's no opponent. There's no other person making choices. The Orcs and Hobbit problem, not game theory. No other person making choices. And as we're going to see, the Monty Hall problem today is also not game theory because there's no other person making those choices. What is game theory would be something like the dollar auction, because your success in the dollar auction completely depended upon the choices of others. So if you entered that dollar auction at $5 and everybody else chose not to bid, well, then you would have massive success. If you entered that auction and you paid $100 and somebody went over top of you and did $105, then you're going to have less success. So the dollar auction is an example of game theory. And the Pirate Booty Challenge revisited version that we're going to do today is also a nice example of game theory as well. So much like we had before, we had descriptive, what people do, prescriptive, what they should do. We have that for game theory as well. So prescriptive game theory is what strategies rational individuals, humans, should do. What is the correct thing to do? And this is based on philosophy, logic, mathematics, etc. And then descriptive game theory is what we actually do. How do we actually play the game? How do we actually interact with others? And that's based on our behaviors. And much like with other decisions and judgment making that we saw, we figure out as psychologists, or try to figure out, what is the prescriptive thing to do. We then go out and actually measure what is the descriptive thing that humans do, and then we try to figure out why is there a difference between those two. So to just kind of show you what difference there often is, last time we saw the original Pirate Booty Challenge, the one where if an allocation was voted down, that person was thrown overboard. And we saw that the correct solution, the prescriptive solution, was for Pirate A to get 98 coins. Pirate B and D get 0 coins. Pirate C and E get 1 coin. That maximizes Pirate A's take. That is the prescriptive solution. And this is from a previous class, but as you can see, we got Pirate A allocation here down on the x-axis. We got the frequency with which it occurred up here on the y-axis. And these bars here, these are the descriptive solution. So this is the descriptive behavior. So this is what subjects actually did. So many of them were completely fair and said, you know what, we got 100 gold coins, 20 for each. Many of them gave themselves just a little bit extra. They kind of said, well, I'm captain, so I'm going to give myself 30, or I'm going to give myself 40, and then I'll split the rest evenly. Only one individual, this was, I think, last year that I did it, only one individual had their descriptive solution match their prescriptive solution. Only one individual correctly solved it. And that is what a psychologist would try to answer. Why is everybody not over here? Why do we have this? How are we thinking? What are our thought processes in order to get that particular pattern? Yep.
So it's normal for us that I didn't get that answer?
Yes.
Okay. Just wanted to make sure.
Yeah, no,
I wasn't missing something.
No, you're not missing anything. It's typical for people to, number one, not be able to come up with a prescriptive solution. And then number two, to fall back on, and this is what we look at as, for psychologists, other strategies, such as our societal feeling of fairness.
Like,
right?
I just gave everyone 20, so there's no problem.
There you go. Yeah, exactly. So that's a heuristic that you use because it's very difficult to solve this prescriptively. All right, so what we're going to do now is we're going to revisit the Pirate Booty Challenge. And to tell us about that, we have our special guest lecturer today, Isabella. So before I let her take it away, just a little background. Isabella is a swimmer for the YMCA Stingrays. She is the current YMCA state champion in swimming, and she won that this year. She is a published author, and she is currently working on her new creation, which is Emily Rocket, which follows the superhero adventures of teenager Emily Rocket here, as well as the day-to-day difficulties that you have when you're growing up. So without further ado, Isabella, if you want to tell us about the Pirate Booty Challenge Revisited.
Thank you. There are 5 rational pirates, A, B, C, D, and E, as we all know. They are doing their end-of-the-year distributions. They have found 100 gold coin treasures. They must decide how to distribute each treasure. The pirates have a strict order of seniority. A is superior to B, who is superior to C, who is superior to D, who is superior to E, as we all know. The pirate world rules of distribution are thus: for each individual treasure, the most senior pirate should propose a distribution of coins. The pirates, including the proposer, then vote on whether to accept this distribution. If the proposed allocation is approved by a majority or a tie vote, it happens. If not, the treasure is thrown overboard from the pirate ship. The most senior pirate makes a new proposal for the next treasure of 100 gold coins. This continues until all 100 gold coin treasures have either been allocated or thrown overboard. Pirates base their decisions on 2 factors. Each pirate wants to maximize the number of gold coins they receive by the end of all 10 allocations. All things being equal, each pirate tries to minimize the number of gold coins that the other pirates receive. Your challenge. Try to maximize your allocation of gold coins.
All right, so thank you very much, Isabella, for that explanation. So,
It's the best second grade reader I've ever seen.
a little bit of a different twist here. So what we're going to do is, this is part of game theory, so we need people to play against. So what I've done is I have printed out Pirate Booty Challenge Revisited sheets. So I will pass these out. There's 5 to a ship. So you will be interacting with each other on this. I'll try to allocate this as best as I can. One of you will be Pirate A, one of you will be Pirate B, one of you will be Pirate C. And then the 4 of you, here, if you guys can be that ship. All right, so you will have to kind of talk to each other, interact with each other, and vote on allocations. So before we go off and running, just a couple of differences between this and the single treasure version. So this version right now, this is a game theory version of the Pirate Challenge. So you are playing against each other. And in the single treasure version, as we've seen, the final allocation is that Pirate E gets 1 coin, Pirate D gets 0, Pirate C gets 1, Pirate B gets 0, and Pirate A takes 98 coins. That was a rational solution for the single version. However, we're now doing 10 runs, 10 allocations. So if this strategy, if this single treasure version is applied to the 10 treasure version, then notice your final allocation is Pirate E is going to get 10 coins, Pirate D gets 0, C gets 10, B gets 0, and Pirate A runs off with 980 coins. But what if Pirate E votes against that single treasure allocation? What if Pirate E says, no, 1 coin per allocation, not enough for me, throw it overboard? Well, in that case, the final allocation is everybody gets 0. Because if Pirate E is going to vote down 1 coin every single time, every single treasure gets thrown overboard. So Pirate A all of a sudden goes from 980 to 0. So if Pirate E follows this strategy, Pirate A has to change her strategy. That rational single iteration solution is not the best solution anymore. So she might say something like, all right, I got my new strategy here. I'm going to give Pirate E 2 coins. I'm going to make Pirate E's situation a little bit better. And notice that at the end of this new strategy, the final allocation, if it's followed, Pirate E now gets 18 coins. So Pirate E has maximized his take through the 10 allocations by throwing that first allocation overboard, kind of sending a message to Pirate A. But what if Pirate E votes against Pirate A's new strategy? Well, in that case, we go right back down to 0 for the final allocation. So what does Pirate A have to do now if Pirate E follows that strategy? Well, she needs a new strategy in which she says, all right, 2 gold coins aren't enough. What about 3 gold coins? What if I do that? So 2 treasures have already been thrown overboard. They're gone. But even so, notice that if this is accepted now, the final allocation for Pirate E is 24 coins. So much better than the 18 gold coins they would have gotten with just 2. And this is just considering Pirate E. But what if Pirate E votes against Pirate A's new strategy? What if he does it again? And what are Pirates B, C, and D going to do? They're not just going to sit there and do nothing. So that's the challenge here. Game strategies can get quite complex. So what I'd like you to do is, Pirate A, you're going to be proposing allocations, 10 allocations, do them one at a time. Every other pirate on the ship, vote on that particular allocation. If it passes, then record that allocation in your treasure list. So how much of the treasure did you receive on that particular allocation? If it's thrown overboard, you put a 0 there. And let's see who can maximize their gold intake by the end of all 10 allocations. So we'll start that up right now. I'll give you about 5 minutes to do that. And talk amongst yourselves, propose an allocation, vote, and follow the rules, and let's see what happens. Yeah. All right, so we've collected the results from each pirate ship. And so this, what I hold in my hands right now, this is the descriptive version of this pirate booty challenge. And actually, I don't know what the prescriptive solution would be, because this is a very complicated game. It's got like 5 moving parts, 5 degrees of freedom, plus you're doing it 10 times in a row. But I can say that the most common allocation, we'll just talk about Pirate A, the most common allocation was around 250. So that was the most common, that occurred in the most ships. Pirate A walked out with 250. So nowhere near the 980 that the single solution would have predicted. And then the highest we got is 570. So just over half of what was predicted. So you can see that adding just a few extra players increases the complexity of this, because each iteration you have to deal with 4 other individuals. Each iteration can be either a reward or could be used as information for further iterations. So you can see that it can get quite complex to figure out what is the optimal solution, what is the best case scenario. All right, so we're going to talk a little bit more about game theory. And I mentioned that a Pirate Booty Challenge that we don't have or I don't know the prescriptive game theory. It would take a higher level of analysis. However, there are games that we do know the prescriptive game theory to it. And those are kind of like the starting blocks that we use to understand the more complicated games. So an example of a game that we do know the prescriptive game theory to is tic-tac-toe. So does anybody in here still play tic-tac-toe?
When I'm bored.
When you're bored? Anybody here play for fun with their peers?
Yeah, sometimes.
Yeah, with your peers. No, okay. So typically nobody plays tic-tac-toe anymore because you played it as a child, but eventually when you were playing tic-tac-toe, you reached a point where every single game ended in a tie, right? Every single game ended with nobody getting 3 in a row. So that's usually when people quit playing tic-tac-toe. And the reason that you got to that point, the reason that you got to the point where everybody tied every single time was because you learned the prescriptive game theory. You learned what you should do. You learned how you should play. And we're able to represent this. So this is an example of the prescriptive game theory for tic-tac-toe. So the way that you would read this plan out is it tells you where to move first. So this big X tells you prescriptively where is a good place to go first. And then it has in each of these, it tells you which square to go in depending upon what O did. So if O moves down here into this area, then you fall into this square. We can zoom in on that. And if this is where you went first and this is where O went next, your best move is to go to that top corner. And then if you go to the top corner and O goes anywhere else but here, well, then your next move is that you win. But if O goes here, then we go in one more time. It's getting a little blurry because it's such a high resolution now. But we go, or high magnification. If O plays there, then your prescriptive move is right there. And you can see that now O cannot block you. You're going to win on your very next turn. So we don't play tic-tac-toe anymore because we know the prescriptive solution. Interestingly, this is called a game of perfect information. This is a game where you are aware of where you are in the game and you're aware of where your opponent is in the game at every stage. So poker is a game of imperfect information because you don't know the cards that your opponent holds. So this is called a game of perfect information. And this is equivalent in game theory to chess. It's just that chess is a whole lot more complicated. So in game theory, there is no basic difference between tic-tac-toe and chess. And the reason is because in tic-tac-toe, you always know where your opponent's at. In chess, you always know where your opponent's at. There's no time when they cover up the board and say, I'm going to surprise you. So you always know what's going on. So it's exactly the same type of a game to a game theorist. The reason we don't play tic-tac-toe anymore is because we now know the prescriptive game solution. The reason people still play chess is because we do not know the prescriptive game solution. And really the mathematical complexity of chess means that within the first 10 games or 10 moves, we're already well beyond what people can represent in their minds. And in reality, any chess playing computer does not have the full prescriptive game theory. But you can prove that a strategy exists in chess where if you're the first person that moves, you will always be able to at least force a tie. There is that strategy exists out there. We just don't know what it is.
Did you ever watch The Big Bang Theory?
I just started The Big Bang Theory, actually.
So Sheldon.
So no spoilers. I'm on season 2.
Sheldon wanted. I don't remember his name. The main guy. What's his name? Sheldon and.
Oh, it's
Leonard. Sheldon
okay.
and Leonard wanted to play. So Sheldon wanted to play chess. So Leonard said yeah. So Sheldon made the first move, and then Leonard started to pick his first move, and Sheldon was like, I can win in 10 moves. I can win in this many moves. So is he just has he played so much, he just knows the strategy?
He has played so much, he knows the strategy. He has played so much that he has a prescriptive, he has the ability to see the prescriptive strategy 5, 6, 7 moves ahead. And basically, what they do when they say, oh, I got, checkmate in 7 moves. What they're saying is that, okay, you move here, right? Let me back this up. So if this was Chaz, they're saying, I moved here, you moved over here, so I'm going to move over here, and guess what? Tic-tac-toe in 2 moves, right? If you get it here, you can be like, game over in 2 moves. That's exactly what they're doing when they're like, oh yeah, checkmate in 7 moves, or 5 moves. But it's, when you think about the fact that you got 32 pieces that each can move, multiply that over 5, you got just a massive amount of possible moves. But in reality, what they're saying is that even your best strategy, at this point, you're going to lose in, however many moves. All right, so now we're going to get to another illustration here. This is to answer the question of whether or not people are rational. And this demonstration is called Guess 2/3 of the Average. And what we're going to do, and you'll play along, everybody here is going to guess a number between 0 and 100. All right, so you're going to guess a number between 0 and 100. And the winner is the person who guesses closest to 2/3 of the average of the guesses. So basically, if we took all the guesses, added them up, took the average, and then multiplied that by 2/3, what would that final number be? That's what you're trying to guess. So to give you an example, if 5 people were playing this game, and let's say player A guessed 50, player B wrote down 47, player C wrote down 76, player D goes 55, and player E says 7. In that case, the average guess, the average of those 5 guesses is 47. 2/3 of that average would be 31.3. So the player closest to that 2/3 average would be player B, and player B would win. So we'll do that right now. I'll give you a little bit of time. So try to figure out your best guess for a 2/3 of the average of the guesses in this class. All right, so I'll give you a couple minutes to try to figure that out. And let's see who can come up with a guess that is closest to what people have found in other situations for this. All right. Yeah, check them out. Yep.
You have to write the number down? Or
Yeah, write down a number.
We're not picking a number within 100, so we're picking the average.
So you're trying to think. So what you want to do in this game, you're trying to think, what are other people going to write down? What number are other people going to write down?
Okay.
Then think about what that average number might be.
Okay.
And then take 2/3 of that average. That'll be your best guess. But that's what they're going to be thinking about you as well. So you can see, no, it gets difficult. And we'll see, and we'll talk about why people tend to choose the numbers that they eventually choose. All right, so does everybody have a number? Okay, so before we take a look at the descriptive solution to this, let's take a look at the prescriptive solution. What is the rational strategy for this game? Well, this is easiest to see in a sort of iterated solution. So if you're sitting there and you're thinking rationally, and you say, all right, the maximum guess possible is 100. That's the highest anybody could go. So guesses between 67 to 100 are going to be impossible, right? Because 2/3 of the average, even if everybody guessed 100, 2/3 of that average is 66. So you're not going to guess between 67 and 100. That's irrational. That's mathematically impossible. So you will then say, all right, guesses between 67 and 100, irrational, impossible. So now your maximum guess for a rational person becomes 66. That's as high as you can go. And then you go again. You do another round. And you say, all right, so now if the maximum guess for a rational person is 66, we're going from 0 to 66, well then guesses between 45 and 66 all of a sudden become irrational. Because if the maximum guess is 66, 2/3 of that is only 44. So the 2/3 average of the maximum guess is only going to be 44. So guesses between 45 and 66 are no longer rational. So the maximum guess for a rational person is 44. But we go around one more time. This is like in The Princess Bride with Vicini when he's like, I'm just getting started. If the maximum guess for a rational person is 44, then guesses between 30 to 44 all of a sudden become irrational because 2/3 of 44 is now 29. So then the maximum guess for a rational person becomes 29. And so on and so forth. And you can do this until you come to the final iteration, the final solution that says that the maximum guess for a rational person is 0. If you're a rational person and you solve this, the prescriptive solution is that your maximum guess is 0. That is the prescriptive solution to this challenge. So, did anybody write down 0? Okay. So you all have different numbers. You all have a descriptive solution. So the reason for that, though, then becomes interesting. Because notice that we came to a rational guess that a rational person would make, which is 0. But there's a big assumption in this. And the assumption is that all your other players are rational. Because it just takes one irrational person to say, I'm going to write down 100. And then all of a sudden, your whole strategy is blown. Because you're sitting there saying, everybody else is rational. Everybody else is going to say, it can't be 100. It's got to be 66. Can't be 66. It's got to be 44. Can't be 44. It's got to be 29. And if everybody does that, then you're going to be correct. 0 is going to be the guess. So that assumes all other players are rational. So if you guessed above 0, there's 2 possible explanations for that. It could be interacting. One is that other players are not rational. So you might have been able to figure out and say, you know what, 0 is a rational solution. But I don't think anybody else here is going to get that. I don't think anybody else is going to figure that out. So then what do? You start thinking, what are they going to do? Are they all going to say 50? In which case 2/3 of 50 is going to be 33. Should that be my guess? So all of these guesses let you know that either players are irrational, so 0 is not the best strategy. So you might have come up with the best answer, if it's not 0, simply based on the idea that other people's are irrational. Or if you assume that other people are irrational, again, 0 is no longer the best strategy. So answers above 0 could be any combination of either you couldn't figure out what the rational strategy was, or you did figure it out, but you ignored it because if other players can't figure it out, then 0 is no longer the best strategy. So one of the times that this was done was in a Danish newspaper, Politiken, and they had their guess 2/3 of the average contest. They got 19,000 entries, and the winning entry, the closest guess, was 21.6. So above 0, far above 0. And notice this is about 3 iterations in, right? This is about people going, you know what, 66, not a good answer. 44, not a good answer. 29, maybe that's a good answer. So that's kind of an indication of how much people can sort of reason through these situations. Because if you think about it, a lot of times when you're dealing with somebody else in a game situation, you have to think about what they're going to do. So you're sitting there and you're like, all right, what is this person going to do? Because I think they're going to do that, I'm going to change my strategy. But what if they know that I'm thinking about what they're doing, so I change my strategy, so then they change what they're going to do, right? What if they know that I know what they're going to do? Well, then they're going to change their strategy. But what if I know that they know that I know what they're going to do? So then I change my strategy. Well, what if they know that I know that they know that I know that they know that I know what I'm going to do? Then they'll change their strategy. I'm already kind of lost. I don't know how many iterations I've gone through. So this kind of gives you an indication that we sort of stop at a moment. We're kind of like, what would other people do? But then what would they do if they knew what I knew? But then what would they do if that case? And that's usually where we tend to stop it. All right, it is Coglab time. So we're going to talk about the Monty Hall problem. Isabella can return, and she is going to take us through this Monty Hall problem, which again gives us a lot of insight into how we think.
The Monty Hall problem, named for the original host of Let's Make a Deal, for not watching the show. Suppose you're on a game show and you're given the choice of 3 doors. Behind one door is a car. Behind the others, goats. Just goats. You pick a door, say number 1, and the host who knows what's behind the doors opens another door, say number 3, which has a goat. Just a goat. He then says to you, do you want to pick door number 2? It's at your advantage to switch your choice. This is Marilyn Savant, known for having the highest recorded IQ, guidance in the Book of Records. And Marilyn Savant had her own
Newspaper column?
Newspaper column.
Mm-hmm.
Savant wrote her first column on the Monty Hall problem that the players had switched, saying that the first door had the 1 in 3 chance of winning. Hence, the second door offered to switch to has a 2 in 3 chance, as the host always opens the losing door on purpose. She went on to explain her answer by asking the reader to visualize the case where there are 1 million doors and the player picks one, and the player picks number 1. Then the host, who knows what's behind the doors and will always avoid the one with the prize, opens all remaining doors except door 777,777. Her conclusion: you would switch that door pretty fast, wouldn't you?
Mm-hmm. All right, thank you very much. So here we have the Monty Hall problem, and this is the little bonus part about Marilyn Savant. So as we saw, she is the Guinness World Book of Records holder for the highest IQ. She actually will not be defeated because Guinness stopped tracking that. So she is literally the last in the record book, the highest IQ ever recorded by Guinness. And she wrote about the Monty Hall problem and reasoned through, gave the prescriptive solution that you should switch. And before we get to whether or not that's actually correct, all right, spoiler alert, it is. But before we take a look at evidence that it actually is correct, what happened after this was published was a very good example, an insidious example, but a very powerful example about sexism and confirmation bias. Because one of the, you can actually find people's reactions to her solution. And many people were against her solution, which is fine, but the way that they were against it is not exactly the way that you should voice your displeasure, and indicated a certain confirmation bias. So I'll read a few of them. Here we got Scott Smith, PhD, University of Florida, and he said, you blew it and you blew it big. Since you seem to have difficulty grasping the basic principle at work here, I'll explain. After the host reveals a goat, you now have a 1 in 2 chance of being correct. Whether you change your selection or not, the odds are the same. There's enough mathematical literacy in this country, and we don't need the world's highest IQ propagating more. Shame. So we can clearly see here definitely a sexist attitude. And when he was presented with that solution, what I would suggest, and what we'll see is a recurring pattern here, was that the solution and the idea that women are not good at mathematics could not be reconciled. So all of these very intelligent people, I mean, you can't get a PhD and not have a certain level of intelligence, but all these very intelligent people took a look at her writing and then interpreted it in a way that was consistent with her own beliefs, that she wasn't as smart as she said she was, or that women are not good at mathematics. So they took this very convincing argument and, like I said, interpreted it, confirmed their own bias that women don't know anything about math, and ended up giving what are completely incorrect solutions. So another individual said, may I suggest that you obtain and refer a standard textbook on probability before you try to answer a question of this type again. Another one, another PhD, I am sure you will receive many letters on this topic from high school and college students. Perhaps you should keep a few addresses for help with future columns. Another one, you are utterly incorrect, and you can notice a pattern. We haven't come to a woman detractor yet. You are utterly incorrect about the game show question, and I hope this controversy will call some public attention to the serious national crisis in mathematical education. If you can admit your error, you will have contributed constructively towards the solution of a deplorable situation. How many irate mathematicians are needed to get you to change your mind? You made a mistake, but look at the positive side. If all those PhDs were wrong, the country would be in some very serious trouble. All those PhDs were wrong. You are the GOAT. This was before it meant greatest of all time. Maybe women look at math problems differently than men. They might. That's not a bad thing. They might. But all of these were highly dismissive. Great example of confirmation bias. They did not want to accept, or they had a personal belief that she was not as intelligent as she said she was. They had a personal belief that women just don't know as much about mathematics. And they interpreted her very rational solution, her very convincing solution, in a way that conformed to that bias. And the way to interpret it to conform to your bias is that her solution was incorrect, and they basically were completely incorrect as a result. All right, so let's take one more, we'll take a now in-depth look to see that she actually was correct. And one of the ways to do this is to actually run this, actually have situations where people choose to switch, people choose to stay, and see who does win more. So once again, we have 3 doors. We have a goat behind one of them. We have a goat behind the other. We got a fine Lancia automobile behind the third. It's actually one of the prizes that was given out on the original Let's Make a Deal. And you need to decide when you choose a door and a goat is revealed, should you switch? Should you switch? Will that maximize your chances of winning that car? All right, so you actually ran this as a Coglab. On each trial, you were asked to pick one of the 3 doors. You were then shown that the prize was not behind one of the remaining 2 doors. Then your task was to choose between whether you stay with your original door, a stay response, or do you switch? Do you pick the other door, a change response? So this is what you would see. You would make a selection, like the yellow door over here. Once you made that selection, the blue door, for example, would open and would show you no prize behind the blue door. You now have a situation where you are allowed to switch. You can either stay with door 1 or switch to door 3. And this is an example where staying with door 1 is the correct answer, and you win your prize by not switching. On the other hand, you might pick the red door, at which time the yellow door opens, shows you that there's nothing there. If you then decide to switch to the blue door, that's the correct one. You then win a prize on the blue door. So again, you can win by switching, you can win by staying, but which one gives you the best chance of winning? Which one will give you the highest probability? So that's what we were looking in this Coglab. So the independent variable was the strategy that you used. So you could either choose to stay with your original door, that's strategy number 1, or you could choose to switch to a different door, that's strategy number 2. Not engaging though. All right.
Hey, I've been standing for a long time.
I know. You want to take a seat? Or you all right? Yeah. Go ahead. Or you can switch to a different door. All right. So the results. What happened? Okay. So here we have the frequency with which you either won or you lost. And here we have the strategy. So did you stay with your original door, or did you switch to the other door? And if you stayed with the original door, the blue bar here is the number of wins that occurred. The red bar is the number of losses. So blue bar, you win the car. Red bar, you win the goat. And you can see that if you stay with the original door, with your initial selection, you're more likely to win a goat. Actually, you're 2 out of 3 times going to win that goat. 1 out of 3 times, you're going to win the car. If, on the other hand, you switch to the other door, and most of you decided to switch to the other door, you're going to win the car much more than you win the goat, and you'll actually win the car twice as often as you win the goat. So this is actual proof that it is beneficial to switch to the other door. You are increasing your chances of winning by switching to the other door. This is what's known as a Monte Carlo solution, where you don't, if you don't understand the math, or if it's too complicated to analyze by logic, you just say, let's do it 100 times and see what happens. And it's called Monte Carlo solutions because that's what they used to do to learn about gambling odds. They used to go to the Monte Carlo casinos and just record how many times does black come up on the roulette wheel, how many times does red, and all the other kind of probabilities. But definitely, switching to the other door is the optimal response. And as you can see here, the percentage of times that you win, if you stay with your initial door, right around 30%, or 1 out of 3. If you switch to the other door, right around 66%, or 2 out of 3, basically exactly what Marilyn Voss Savant was saying. All right, so any questions about the Coglab and the results that we get from the Coglab? All right, so we're going to wrap up today's class with one last little mention of Marilyn Voss Savant. So as we mentioned, she's the smartest highest IQ ever recorded. And it was very interesting when I was doing this research on her. I came across an article that came to her defense, right? So it was an article that came to her defense, and it goes, the time everyone corrected the world's smartest woman. And notice that even somebody that was coming to her defense, Zachary Crockett over here, even this individual still revealed a bias that they had. They still revealed a sort of implicit bias that they have in their beliefs, in their propositional networks, in their knowledge structures. And you can see it in the title here because he called her the world's smartest woman. That is not true. She is the world's smartest person, right? So nobody ever says something like, well, you know, Tiger Woods, he's the greatest male golfer of all time, right? LeBron James, he's the greatest male basketball player of all time. They just say, no, greatest golfer, greatest basketball player. And again, even somebody coming to her defense still kind of showed that implicit bias. And this is one of those things where, you know, part of what we have in society, everybody is aware of the stereotypes. Part of what we have in society, it's incorporated into everybody's thought processes. And one of the things that I think we're seeing in our society now is when people are trying to go towards more open-mindedness, more acceptance, more diversity, more integration, they're still dragging behind all of those preconceived notions and all of those biases. So we are in a very interesting period right now that is ripe for psychological research because we're in a transition period where people are trying to make this leap. And even this writer here, he tried his very best, but still couldn't help but reveal that he still has a little bit of that implicit bias. So, you know, opportunity for psychologists to study those thought processes, and also just a little, you know, thing to keep in mind when people do make errors, when people do make mistakes. And I've seen this on social media, you know, over and over again. Maybe don't jump down their throats immediately, especially if they're trying. And, you know, let's give ourselves all some time to reprogram our thought processes. Any questions before we wrap it up for today?
It's funny that her last name is Savant.
Yeah, I know.
It's
I
very
know.
ironic.
It's like, yeah, she might have. Yes? Oh, yeah, go ahead.
Okay, get ready for this.
Okay.
Mary Voss Savant reminded you of anyone
So is there any popular character that Marilyn Boss Savant reminds you of?
Like in a TV show?
Like in a TV show. I'll give you a hint. In a Disney. It's a Disney movie.
I was thinking of Psycho.
I was thinking
Oh,
of
you're
Friends.
thinking of Elaine?
I was thinking
Yeah,
of Friends.
a little bit.
Kind of looks like.
Is it live action or animated?
It's animated.
Is it from it is from Tangled.
Yes,
The
it's
mom.
Mother Gothel
The
from
mom. I was
Tangled.
like, the mom.
Better than Mother Gothel. I was like, is this Mother Gothel?
Well, she looks like Mother Gothel
I guess
after
like
the
she-
song is sung,
Okay.
right?
All right,
After
I'll
the
give it to
flowers
you.
gleam
I
and
was
glow
like,
song.
I know
is
my
sung.
Disney movies.
But yeah.
Tangled is a good one.
But I like the fact that it kind of fits in. Like Marilyn knows best. Listen to your Marilyn. It's a biased world out there. All right, so that is it. That is all. That is what we have for this semester. So if there aren't any other questions, that's what we wanted to cover for this semester. So
How many
thanks for
classes are you
coming
taking?
out. And we'll see you at the exam. And thank you, Isabella.
How many classes are you teaching today?
I have no idea.
You don't know your schedule yet?